I mentioned in the previous videos that a lot of the syntax that you're used to from C transfers almost directly into C++. And in fact, if you're coming from a language that isn't C, then it's still likely that a lot of the syntax transfers, because many languages, including a lot of the languages people learn in first programming courses, like Java or Python, owe a lot to C. They're actually descendants of the C language. And so you get a lot of the structures you're used to from C in those languages as well. So those of you that know a language like C or Java or C# especially would look at code like this and see a lot that looks pretty familiar. So you can see this C-style while loop, and there's a C-style variable declaration and initialization. There's a C-style for loop. And in fact, you'd see pretty much identical while and for loops in a language like Java. The only major difference between this piece of code and the equivalent C code, so code that may have come out of the second or third week of CSC 111, is this. Which of course we know is the idiomatic C++ output formatting, using that stream insertion operator and the standard output stream cout from the standard library. Now I should add that in fact we can make this code look even more like C code but still valid C++. So it turns out that this thing here, the customary standard output stream cout, is part of the standard library. It comes in via this thing, iostream. So unlike in the C standard library, the C++ library does not use .h or .hpp in the headers. So iostream is what you bring in for things like cin and cout. But it turns out that the entire C standard library is actually part of the C++ standard library. You are allowed to bring in parts of the C standard library if you want to use them. And we're going to do that in a couple of videos. Not for what I'm discussing here, but for something else. Because there are parts of the C standard library that are still very useful in C++. Simple functions like asking if a character is uppercase or lowercase, the C version of those functions is perfectly valid. Why not use that? Why bother creating a new version in C++? And it turns out that you can bring in parts of the C standard library like printf. If you really want to use printf, you could do so. You could bring it in and use it in this program. Now the reason we're not going to do that is, although it would work for this program, you can still use printf to print out ints and floats and things. Printf has huge limitations in the data model of C++. And that means that one way or the other, we're going to have to use this output formatting notation eventually. We might as well just get used to it now. Although it's a bit clunky, it'll never be, I think, as terse and easy to get, once you're used to it, easy to use as printf. Printf has a lot of conveniences this format does not. The issue is printf has some limitations that this format does not, and they're limitations that are going to become serious restrictions on us later in the course. So we're stuck with this. But the key thing is, much of the underlying control flow is exactly the same in C++ as it is in C. And in fact, even stuff that's not pictured here, like the existence of functions, you might have noticed that int main looks a lot like a C program. There's still a return statement. A return statement you might be used to from C or from Java or other languages. It turns out that we can write functions in C++ in much the same notation as in C. Let me run this program though. So this is a program that uses two different forms of the same loop, so both a for and while version of the same loop, to print out squares of numbers. So the squares of everything from 0 up to 4. It does it with two different ways. We can see the same output twice. Okay, so we were able to do that. The reason I want to talk about this is both to demonstrate, again, that we're not completely in the wilderness as far as syntax is concerned. A lot of that C stuff is still a benefit to us. But there are some places where, because C is a simpler language, it never had to contend with certain strange philosophical questions that are in fact a very big deal in C++. So one of them is this. It seems odd. It seems so innocuous. But we have to talk about what this actually means. So line 11, if you're used to C, line 11 appears to be saying, make a new variable called I with an initial value of 0. So make a brand new variable, the same way that I might be doing that on line 18. Make a new variable called j with an initial value of 0. And you might recall from CSC 111 that I could write line 11 as either int I equals 0, or int I, and then on the next line, as the next statement, I equals 0. Make a new variable containing nothing in particular, and then on line 12, use an assignment statement to store the value 0 into that variable. The question, though, the philosophical question we have to answer in C++ is, does this mean the same thing as what I had a minute ago? Are those two sides of the same coin? Are they two forms of exactly the same operation, or are they separate operations? And I think that, in fact, in the C context, it's meant that they be viewed as basically the same thing. So whether or not I use two separate lines for it, what I'm doing is I am creating a new variable and then giving it its very first legitimate value with an assignment statement. And the rules of the assignment statement apply whether or not I do it all in one line. It turns out, though, in C++, it's actually a very big deal, especially later in the course, the difference between creating a variable with a particular value that it had at its creation versus giving a variable a value via assignment. And we're going to notice that not only is it a philosophical question for today, but later it turns out to be a very thorny issue because there are some variable types where you're not allowed to give them a new value later. So giving them their initial value is special in some way. And therefore, we should maybe find some notational way of treating that as a special operation. I would argue that giving I its initial value of 0 is a bit different than later overwriting whatever's in there with some new value. It's not as important to care about that distinction for ints and floats, but it's going to be important later in this course with other strange exotic types of data. And so one solution to that is that the language has defined something, a different syntax to use for the special case of giving a variable its initial value, for initialization, or what you might call later construction of the variable. And it's a syntax called uniform initialization syntax. We're going to need to use this no matter what. Although you are allowed to get away with writing C-style initializations, I'm going to try to avoid it in this course. You're allowed to do it, but you'll notice that there are cases where you simply can't. You have to use uniform initialization. Therefore, I would argue you might as well just learn it and start using it consistently now. It'll make it a lot easier to use it later. So here is C-style initialization, and we're going to come back to this example in a few minutes and fix it up a little bit to use the uniform initialization syntax. But first, let's walk through using a few different types to remind ourselves of the benefits of uniform initialization. So here it's saying create 3 variables with these values, and then later on I'm going to try and print them out. So down here I try and print all the variables out. Because I haven't yet created them, we can try compiling this and observe that the compiler will not be at all happy if I do that. So there it is. And it gives pretty predictable compile errors because I don't actually have variables I, j, and g. So the first thing I want to do is create them. I will use C-style initialization. So int I equals -116, unsigned int j equals 6, and double g equals 10.187. Now we're going to have to get used to using this odd-looking type, unsigned int, in this course. We're going to need it a lot. In 111, in the C course, we didn't spend much time on this type at all. We basically never discussed it because we didn't need it. At the time, we were mostly concerned about the difference between integers and real numbers. In this course, we need it for a few reasons, one of which is that we need to have a more sophisticated view of data, and the other one, a much more urgent one, is that the language sort of forces us to. Even in the next video, we're going to need to use it because the compiler is going to start complaining if we don't. So what is an unsigned int? A normal integer variable can contain whole numbers in some restricted range. The typical range of regular int would be approximately -2 billion to +2 billion. And it can store whole numbers, negative, positive, or 0. An unsigned int is an integer value that cannot be negative. It can be 0, but it can't be negative. And in exchange for getting rid of all the negative range, you get a bit more positive range. So int has range approximately -2 billion to +2 billion. Unsigned int has range 0 to about 4 billion. I think it's about 4.2 billion. It's a power of 2. And so that's one advantage of unsigned int. If you know that your variable will never be negative, you can use unsigned int to get some extra range. Another clever reason to use it is, what if the thing that you're storing in the variable, whatever the variable represents, what if that would never logically be negative? So an example being the length of a sequence or the size of an array or something. Well, an array can't have a negative number of elements, so why don't I use unsigned int to store its size as a clever cue that maybe this is a number that would never reasonably be negative? It's actually a way of sort of improving the readability of your program. It makes it obvious to somebody reading the code that there's an intent that this variable never go negative. So one way or another, whether you like that argument or not, we will have to use unsigned int in this course. And then there we have double, and we know already double is a way of storing real numbers. Okay, so these are C-style initializations, where I create a variable and in one line, but essentially in a separate operation, appear to be assigning it the value that is then its initial value. In a sense, we might diagram this out. If I'm drawing my boxes, I would say, well, I'm going to make a box for I. Then I do the assignment statement. I go get the value. Let's see. So on the right-hand side, I have -116. So I store -116. And the key thing there is that I create the variable, then eventually put something into it. And the rules of assignment statements do still apply. Now, we'll notice later on that one of the reasons we like avoiding C-style initialization is that what I just said isn't entirely true for some very complicated cases. The language has had to evolve a very odd way of doing this strange C-style initialization over the years. One of the great reasons to use uniform initialization, what we're going to see in a minute, is to avoid having to think about the implications of C-style initialization on complicated data types. None of these types are complicated enough to worry about it, but it is something we want to worry about later if we didn't have uniform initialization. So I'm going to comment these out. Actually, I guess I'm going to prove that the code runs and then comment them out. So I compile, I run it, and then it prints out the values. I is -116, J is 6, G is 10.187. And we can see there, if we look at the print statements, it's printing what we expect them to print. Okay, so task number 2. I want to comment these 3 out. This is yesterday's news. In this course, we would rather avoid the C-style initialization, although, as I said, you're welcome to use it in my course. I don't know about other people teaching C++ out there. I don't mind if you use that. However, the sooner, I think, at least in my opinion, the sooner you build the habit of using uniform initialization, the easier it's going to be, because you will need it eventually. There will be places eventually where you can't use C-style initialization. Okay, so I would like to initialize the same 3 variables with uniform initialization. And I do that by using curly brackets. Now, the key thing to observe here is the curly brackets are only for initialization. If I want to change the value of I later, I would still use an equal sign. I still do an assignment statement. But the curly brackets are a notational device, if nothing else. A notational device that lets anybody looking know this is supposed to be the initial value of a variable. I don't want all the rules of assignment statements to be applied. I want the variable I, at the moment of its creation, to already equal -116. And then unsigned int j gets the initial value 6, and double g gets the initial value 10.187. And that's it. That's uniform initialization. Whenever we create a variable with an initial value, we put that value in curly brackets instead of using an equal sign. That's it. If we ever want to change the variable, we still use an equal sign. As I mentioned earlier, we don't have the option of using curly brackets to reset the value. The curly brackets are now a special notation just for initialization. And even in the next video, we'll notice that that comes in handy, that there are certain things about initialization that are special that an equal sign can't quite do for us. So I'll run this to prove that this works. And it does. And then I want to talk about, again, there are some things about uniform initialization, some benefits it has that are very hard to unpack just yet. We have to know a lot more about what data really is in C++. I think I can prove a couple of things about uniform initialization that allow it to earn its keep, at least for now. So one of them is this. I'm going to comment out my declaration of I, so I can talk a bit in task 3 about all of the ways that I could declare variables back in C. So one of them is, we're used to writing something like this, our C-style initializer. What about this, though? Int I with no initializer. And we should recall, in C++ as in C, what this does is it creates a variable I, but does not do anything to the memory. And I'll try running this, and then we can see what we think about the result. And the compiler here gives us a warning. It actually says, are you sure? You're using the variable I, you're reading its value before you've actually put a value in the box. Are you sure? Yes, I'm sure. For today, I'm sure. The value of I is apparently this. I made a variable called I didn't put anything in the box, and then when I looked inside the box, there was some junk in there. And the reason for that is that when I hit line 37, the compiler reads this as, oh, make me a box for a variable called I. There it is. There's my box. It's an int. Great. What's in the box? Well, I never put anything in there. And I just get a space in my computer's memory. And if I go looking inside the box, because nobody cleared it out, It's just got whatever was in there when the last person was done with it, whatever garbage they left behind. Now, it turns out that really, especially on machines like the Jupyter Hub virtual machine I'm using here, it's actually surprisingly common for the junk that got left behind to just be the number 0, which of course gives you a false sense of security because you think that whenever you declare a variable without giving it a value, it defaults to 0. As we can see, that is not the case. We get some strange random number. If I run the program again, I get a different random number. And in fact, it's not quite clear what's going on, although there is a bit of a pattern. It seems like it's around the same value each time, but it doesn't go uniformly up or down or anything. It just sort of hovers around this same strange value. But it's clearly not reliable, and it's definitely not 0. And the issue is, of course, just that the variable is uninitialized. If I want it to have a particular value, I need to give it that value. In a language like C, if you create a variable without giving it a value, you are telling the compiler that it should not do any more work than just making you a place to put something. Because if it were to go and put the number 0 in this box, that's taking time. That takes work. You didn't ask it to do that, so it won't. And so, of course, we should never use uninitialized variables. And although there are reasons the compiler does that, I mean, there are reasons we don't want to do the extra work. In a course like this, my recommendation is always, well, if you want it to have a value, just always give it the value 0 if you can't think of anything better. Do something to it to give it a reliable value. Because if you don't, then the program could have random behavior and you could spend hours trying to debug it. Okay, so of course we know the solution. If I want it to have the value 0 or whatever, I could just initialize it to be 0. So we'll try that for completeness. And sure enough, there it is. But there's sort of a neat feature of uniform initialization, which is, okay, so I know that a good, sensible default value for an int, that's 0. Same with a double or an unsigned int. 0 is a good default if I can't think of anything else. But in this course, we're going to work with a lot of very exotic types. Types that we don't fully understand underneath. Like, we know how to use them, but we don't quite know what they really are. And that means there might come a time that we work with a type where we don't quite understand what a good default value would be. And so it turns out that uniform initialization actually gives us a clever trick to work around that. What I can do is leave the brackets empty. If I provide curly brackets, but I leave them empty, what I am telling the compiler is I want the variable initialized. But I don't really care what it gets initialized to. I just want it to be whatever the sensible default value of this type is. Let the type decide. So the compiler is now going to construct a default int, whatever the default int value is going to be. It lets the int type decide what that is. Of course, it turns out that the default value is going to be 0. The int type has decided that its default value is 0. So I'll save that and we'll just prove that point. It turns out for all numerical values, if I use empty curly brackets, I get a default value of 0. And that's great. And you could stare at that and say, but that makes no sense. Why not just put the number 0 in there? Like, what's the point of this party trick? And the reason is there are other types you could work with that aren't numbers, where you can't just put 0 in there. They can't store a number, but you want them to be initialized with whatever makes sense as a default. So you let the type decide for you. You leave the brackets empty. And that's a very useful feature of uniform initialization. And if you stare at it, you realize there really is no alternative with C-style initialization. How do you use an equal sign? If you don't know what you're going to put on the right-hand side, what do you write with a C-style initializer? Uniform initialization has a solution, and it's the empty brackets. Okay, so one more thing. Suppose that I create my int I and I set it to be 0. And then later, when I'm working with so I do some work, we'll pretend I did some work here. Later, I decide to set I to be some 3,141.592. And you might recall from C or whatever previous course you took that if I do this on line 43, I follow all the rules of assignment statements, I get the number that I end up with on the right-hand side, and then I try and jam that into I. But I is an int. Oh, I don't paste, whoops. I is an int, and that means that I have to throw away everything after the decimal point. So I'm allowed to do this. In C and C++, I'm allowed to take a float or a double and jam it into an int. But if I do it, I'm coercing, I'm doing a conversion, coercing the value of the float into the int. And a coercion requires modifying the data. So what I end up doing is just storing the number 3141, because I can't store a decimal point into an int. So we'll try that out to prove the point. And that's valid. I am allowed to jam a float into an int if I want to. And it makes sense. I might have an int and do some work with floats and then have to store a float into my int variable. And that's why the language allows it. Me to coerce without any further, without having to waive liability or anything. It just allows me to jam a float into an int. But what about this situation? Here, I'm creating a variable and trying to assign it a value it can never contain. So I'm not just working with an int and then at one point decide to store a float into it. I'm making an int, and in the line where it's created, I've added this sort of odd contradiction. I want it to be an int, but I somehow want it to have this value, which makes very little sense. Maybe the reason I did this is that I made a mistake. Maybe it's a typo. Let's try this with C-style initialization. Int I equals 3141.592. And the compiler puts up with it, and I get the predictable result. The int is just going to be 3141. But again, why would I ever need this? Why would I write a numeric constant with a decimal point and then assign it to an int on the line the int was created? Well, it's possible it's because I've made a typo. I might have forgotten that I didn't need an int. I might have meant for this to be a double. Or maybe I want to do something with this number. You'll notice that it didn't get rounded up or anything. Maybe I don't recognize, I just don't notice that this cannot fit in this variable. And again, it's valid to assign a float to an int, but do you really want it on the line where you create the int? And so if I use uniform initialization for this, actually I should first say what happens if I don't. So if I use an equals sign, I have to, a C-style initializer, I have to follow the rules of an assignment statement, which say, if you want to, you can assign a float to an int. If I use uniform initialization, that's not an assignment statement. That's special. That's just for initialization. And it makes very little sense that I'd want to initialize an int to be this value with a decimal point. And because the curly brackets are specifically for uniform initialization, the compiler can now read into it a little bit more. It can say, hold on a minute, this thing here is a double. Normally a numerical constant defaults to being a double. This thing is a double. Why are you trying to put that in an int? You're making an int to store this strange double value. That makes no sense. You're going to have to get rid of some data for that to work. You're going to have to narrow the data. It's a narrowing conversion. That makes no sense. You can't do it. The compiler is generating an error here to help me catch a possible mistake. So I can go up and say, oh, that's right, I wanted that to be an int. I'll just make that an int myself. Or I could say, oh, wait a minute, that was supposed to be a double. And by doing this, the compiler is now able to give me more feedback than it would otherwise. It has to let me assign with an equals sign a float to an int, but it doesn't have to let me initialize a float, an int to contain a float value. In this case, I guess I do want it to be an int, so I'll set that back to this. And so you might look at that and say, well, what's the point of that? Making the compiler give another error? Like, why would I want more compiler errors? And one thing you might want to, I guess, recall, if it's been a while since you programmed, is compiler errors are the best errors. If your code doesn't work properly, what would you rather have to do? Debug it by hand for hours or have the compiler tell you that you made a mistake? I know which one I would choose. I would like nothing more than for my errors, the mistakes I make, to be compile errors. And so anything I can do to get the compiler to give me more feedback, to generate more errors, is help, because it's less time I have to spend manually debugging my code. And so this is one reason why using uniform initialization can pay some dividends even right off the bat before we've begun working with complicated data types. So I'll just compile and run this one last time to wrap everything up. And then when I go back to the example I had earlier, okay, so there it is. I've got I equals 3141. You actually might have noticed earlier that when I printed out the floating point value 3141.592, it only printed with 2 decimal places. That's because of the default formatting of the way doubles get printed out. And so keep that in mind. It is, by default, the language wants to use a certain number of significant digits. Just like with printf in C, you can change that, although it is a lot more cumbersome to change that in C++ than it is in C. Let's go back to this example. So here in this example, I was using C-style initialization for everything. All I want to do to wrap this up is just revise these to be using C++ style uniform initialization. So I'm going to use that with my curly brackets. And then down here, I could use curly brackets as well. So I'm going to do int j, curly bracket 0 as my initializer. Now, as I said, C-style initialization is valid in C++. You're welcome to use it. It's good to get into the habit of using uniform initialization as often as you possibly can. I try and do that. I don't even always succeed. I often write for loops with C-style initialization. But if you build the habit early, it's a habit that'll stick with you and make things a lot easier later on. So we'll try recompiling this with that modification. And there it is. It generates the same output as before.